Alrighty, hey there, folks. We're going to go ahead and dive into our last module where we're going to be talking about rasterization from the software perspective. You'll have a lab and then a homework that'll be released just a little bit later on this topic, and we'll wrap that up. And then we'll be moving on to regular OpenGL with our taking advantage of hardware acceleration after this. So this is another fun one, another fundamentals. So let's go ahead and dive into the fundamentals of computer graphics with our Rastration 3 and talking about transformation and viewing here. Okay, so I'm just going to go ahead and jump into the slides. As always, don't forget to do your in-class activity within a week of this module. And let's go ahead and dive in here. So a little pre-class warm-up, and this relates back to the readings, but I think the essence of linear algebra is a really nice series for you to be reading or rather watching along with these first few modules. The particular chapters or the videos 3 through 5 are particularly helpful, but I would still recommend at least watching the first ones just to get the sort of setup for the particular topics that they discuss. So really nice series, really great way to visually get the intuition behind what we're going to be talking about. Okay, so with that warm-up, I also want to introduce another pioneer of computer graphics. This is Dr. Rebecca Perry, and she's known for her virtual reality work in real-world applications like Wafer. So for folks who are familiar with that, or unfamiliar rather, that's a furniture company, and they do a lot of sort of simulations and stuff so you can see what furniture looks like in your house before you buy it. So you can read about Dr. Perry's bio here. I guess it's not here. Let me relink that. So now you can see the profile and just hear a little bit about her journey as she accomplished or put to practice some of her 3D work during her doctorate. So some cool stuff there. All right, so with that said, the link's now fixed for you guys by the time you see this. Let's go ahead and dive into our lecture. Again, the course logistics, assignment 2 is a little bit delayed because it's a little bit more infrastructure heavy, so I'm carving some pieces out to make it reasonable. But lab 4 is also out, and it'll make sense to do lab 4 just a little bit before assignment 2. The other note that I want to make is I'm working on or contemplating just releasing all of the content for this course, or at least a preview of it. I might still edit a few things here or there, but for some folks who are currently working full-time or on co-op, it might be advantageous just to have all of the content. So if you happen to have during the weekend, if those are when you have large chunks of time to catch up, you can. I'm willing to try that out as an experiment with the note that some of the content might change a little bit, but largely I think I have most of it done to the extent that I want to. And with that, I will also contemplate releasing the final project specifications early as well. So you'll be able to take a look at that. All right, so just a note there on the logistics. Last lecture, we talked about linear algebra, or the sort of linear algebra that we would need for this course, or at least reviewing a few of our tools. So some different formulations, like computing the magnitude or the length of a vector, what a vector is, certain properties, how we add them, subtract them, multiply, non-uniform multiplication by a scalar and a vector, midpoint formulas, and then we wrapped up talking about matrices and some of the matrix math. And we're going to resume with this a little bit today as well, just to make sure that we sort of understand these concepts and what we're doing, because this is going to repeat not just for our software rasterizer here, but also for our hardware stuff that we do with OpenGL. So it'll be good to see these concepts, understand them, give you a little bit of time to catch up and read the resources that have been provided, as well as the presentation today. All right, so diving into it, we've been talking about graphics, the graphics pipeline a little bit. And again, one way to think of it as, our screen that we're looking at is our screen into the 3D world. So sort of like a screen door, we used that analogy previously. But so far what we've been doing is just slowly building up this graphics pipeline in our software rasterizers. So last time we really got as far as a rotating triangle, which is pretty cool because at that point we have stuff that's in 3D. But we want to understand a little bit more of what's going on there. And that'll be part of the assignment that I provide, just so you can, again, try to get some intuition of what's going on as well. And today we're going to really want to look at a little bit more of the mathematics behind each of the transformations and the different stages of the pipeline. Okay, so again, a simple graphics pipeline, and this is sort of what we have so far, is really going through 3 stages here, where we have our sort of application, where we define sort of our geometry, our models, and so on. And then we move to the next stage where we're navigating our world with a camera. Our geometry is being translated and rotated and moved in different places. And then we get to the final stage of this pipeline where once we've moved everything around, then we want to start shading it in. And adding lighting calculations, and that's the final scene that the user sees. Okay, this rasterization stage. Okay, so again, just to put concrete, images to each of these steps in the graphics pipeline. Again, this is the application stage. So this would be sort of a 3-stage pipeline here. It's just your models. So your triangles that you have, any data in your graphics applications, and so on. The next stage is your camera and model transform. So again, the model, you can kind of think of this, this is really your objects moving around here, and then you're transforming them with your camera, or where you're viewing these objects in the world as you move around, right? This is you. You're the camera or the eye in this scene. And then the final scene is what we've been working on a little bit with when we implemented the rasterization algorithm to fill in our triangles, okay? So determining which pixels that we actually fill in our program. All right, so let's continue on talking about those, this sort of rasterization part here. So this is sort of the third part of rasterization on our great looking render, this sort of tool here. And so far we've been working on implementing this great looking render and gotten as far as filling in triangles. We've learned some of the math, some of rotations, and so on, or at least we've seen them and applied them, so that we can start getting some intuition as to how these things work. Okay, so let's revisit our fixed rendering pipeline here, right? All these stages here with our software render, and recall that our real goal is that we're starting here at this vertex data stage here. And we're trying to transform just a single vertex, or rather 3 vertexes that make up 3 line segments, which make up a triangle, and sort of populate or push that data through this pipeline, and then ultimately see at the very end in the frame buffer, which is just a fancy way of saying, the image that we see on the screen, we want to be able to see that image, okay, of our triangle, okay, all the way through this pipeline. Okay, so let's take a little look at the a vertex's journey from 3D to 2D. Okay, and maybe another way I can edit this just to make it a little bit clear, from 3D X, Y, Z to 2D X and Y on your monitor. Okay, that's really what I'm saying here, just to be really explicit about it, because we're going to specify our points in a 3D space, or 2D we can do as well, but really in this class we're doing X, Y, and Z, and then we want to see them on our monitor somewhere. Okay, so there's this stage that we didn't talk about last time, and or rather 2 modules ago, to jog your memory, the transform and lighting stage. And I want to at least talk about the transform stage right now and discuss this. Okay, so the first stage in this transform process that I want to talk about is we are really working with plotting our vertices in one at a time, X, Y, and Z. So this would be for our cube, the individual vertices, the 8 vertexes that make up a cube. And we're specifying them in local coordinates. So we're not worried about where they are in the world, but here's sort of a cube, and it's centered around the origin, and we're just plotting points here, offset by 1 from our origin. Okay, to make our cube, and we call that the local space. Okay, so this is the first part where we're just here's some raw data. Here's how to make this object here. Just makes things easy to work with. We don't have to worry about the graphic scene. Again, we're just plotting points in our scene. Okay. So again, the transform stage, again, it's going to consist of many different other steps, and some of them are going to be marked as optional, but let's take a look again through this, okay? Okay, so starting here, again, at local coordinates, here's our points. As I mentioned, the 8 points on a cube, or 8 vertices. And then the next stage is to take those vertices and move them into what's called world space here. And actually, let me make this bold because this will be an important term that comes up again. But what does world space mean? Well, it means, where are your vertices in terms of the world? And you can think of this as, if you want, is, as a person, right? So pretend, you have your cell phone in your pocket, and everybody's got one. So you've got a coordinate somewhere in the world, X, Y, and Z. The GPS knows where you are. So that's your sort of world space. The origin might be the center of the Earth or the core of the Earth, and then we're all sort of offset from that position. Okay, that's us in the greater world space. Okay, now how do we get there? Well, you could imagine all of us starting. Take me and your 40 plus classmates here. We all start at the core of the Earth, the center of the Earth, and then how would we transform, that is, move to our current locations? Okay, and how we do that is, well, we would have a model matrix. So you can think of this as just a transform, maybe a translate, so that moves us somewhere, or rotates to get us in the right orientation, or scale us, or whatever. And we'd multiply this model matrix times our local coordinates, and that puts us into the world space. So it's moving us around in the world. Okay, and there's various ways that we can move around. We briefly introduced them last time. Translate, rotate, scale, and we're going to introduce those terms again, just as review this time. Okay, so once we've moved stuff around, then the next stage is to consider is the view space. Okay, so this is sort of, you'll see at the start of these, so doing the world to camera transform is the first stage of this. And that is to say, okay, now that we're all moved around in the world somewhere, and I'll turn on my camera for this so you can see me, because that's exactly what I'm talking about. The view space is sort of your camera. Right, so I've got my webcam here. I'm going to point to it and cover it up just for a moment. But if I move that camera around, and imagine I'm fixed, I'm not able to move, well, the camera's changing where I sort of am, the perspective, if you want to think about it that way. So that's what the sort of viewing space is. Our eyes into the world is, my webcam or your webcam. It's the camera. Folks who play games, this is the camera that's viewing the action, right? Folks who watch movies, hopefully everyone, this is the film crew that's, filming the Avengers or whatever, live action movie. That's what's going on in the view space. So how we perceive the world depends on where our camera is, okay? So this will be another matrix that's called the viewing matrix that we multiply through, and that tells us, well, where are we in the world? So we're sort of moving, so we specify, again, just to recap, where all of our points are on a cube relative to the origin. Then we shift this cube somewhere in the world, and then we move our camera around, which is viewing this cube, to see, where are we going to view things in our world, okay? Okay, then the next step after this, also related to the view step, is the perspective transform. And we'll talk about this a little bit, but this is the idea of, how will we, again, see the world, but what's our sort of field of view? Okay, and by this, here's sort of the analogy. You'll see me use it probably a couple times, but it's sort of this idea, if you're standing on train tracks and you look down the train tracks, you'll see that they converge to a point. Okay, and this is what gives us perspective, right? This is how we as humans see. So objects that are far away along this train tracks, they appear smaller, and they'll actually appear to converge here, okay? because they're getting smaller and smaller and smaller as you view along this line of the train tracks, because you're getting farther and farther away. They're not getting closer, right? If you actually walk this train track, they should be evenly spaced, but this is just how we perceive perspective. And by having perspective, that gives sort of volume or 3D in our scenes, right? The same way it does in the real world. Okay, so this is actually what you're going to be solving for your lab 4, the perspective problem. And you'll see how it makes a difference in this sort of star simulation here. And let me actually transition to that just so you'll have an idea of what's going on here. So if we go into our repository, to lab 4, and I'm going to build the lab, just so you can see. And if I run it, pop that on the other screen, you're going to see these flickering stars here, okay? These are just stars that appear and reappear. And there's no perspective here, so you can't tell where you are or what's going on, okay? How far away they are. They all appear just to be the same distance away, okay? And I'm just randomly positioning them so that they appear over time or move. Now, what you're going to want to do, or the implementation that you're going to do, and let me go ahead and open this up so I can show you a solution for lab 1, or excuse me, lab 4, is you'll create actual perspective here. And if you create perspective, it'll look like you're moving through this star field here, okay? So you'll have this sort of flying effect. You'll feel like you're moving into it. And this is by appropriately rendering these stars, which some should they're randomly generated, appear further away from you, and you're sort of zooming through them, okay? So that's a kind of neat perspective trick here. Okay, so that's what you'll be doing for your lab here. Okay, figuring out this perspective problem. Now it's worth mentioning along this stage, there's other types of optimizations and things that occur at this stage here, 8A. If an object's not in our peripheral vision, right? So if something's behind you in the world, we don't need to render it, right? So we call this clipping, or if there's an object that's only partially visible, we would sort of clip it. So that's an important part of computer graphics clipping, because it's an optimization, right? We don't have to draw things behind us or that are only partially visible, right? Your peripheral vision, and let me again come to the screen here, is what you can see. You can't see anything behind you or to your side. We have about it depends on folks, I guess, but say 120 degrees or something like that field of vision. Not really the full 180. We can't see behind us, right? So we don't have a 360 degree field of view. It's limited. So anyway, that's the idea of clipping space. We're not going to really worry about that for too much stuff here, and OpenGL is going to take care of that. But this is something we could add to our software renderers. Okay. And then finally, once we've done that, once we have everything in perspective, we can project our points onto the screen that are visible. Okay, so the vertices go through this process, and they are normalized to a value between 0 and 1. Okay, so that is the sort of pixel locations will be 0 to 1 in the x-axis and 0 and 1 in the y-axis. And then we map those to however big our window is. So if our window is 1280 by 800, we just map, so 0 would be 0, 0. A full 1.0 value in the x-axis would map to 1280, okay? And then we rasterize things, okay, using the algorithms that we have already built. Okay, so we've already done sort of the hard part in that sense. But as you can see, the journey, this journey to take a 2D point to a 3D point, it takes some time here. And these terms are going to keep reappearing when we talk about modern OpenGL. So it's worth seeing them now again in the software render, implementing it a little bit in our code, and playing around with these values just to fully understand what's going on in the graphics pipeline. Okay, again, it's useful to know what's going on in the graphics pipeline because then you know where to debug, which stage an error might be happening, and so on. All right, so with that said, let's go ahead and dive into transformation and viewing. Okay, this is sort of our math foundations too. For folks who are wondering what this visualization is, this is from that linear algebra series that I keep pumping up, the videos 3 through 5. It'll show you how a matrix multiplied through a point is actually moving it. You can sort of visualize it in a Cartesian space. Okay. So this will be a little review from last time. I'm just going to fly through this. Recall last time we talked about points, lines, and triangles that make up our scenes. Very simple, primitives that we have, but they can be used to approximate nearly any shape that we have here. Okay, so this is all review from last time, and then we talked about the rasterization. Okay, so again, what we've covered so far is part of the larger fixed function pipeline. This is part of our great looking render, our own API that we're building or sort of messing around with some of the code. So that's what we have thus far. Okay. Some of the challenges that we had, again, reviewing these things like the painter's algorithm, so figuring out which objects to draw sort of back to front. We discovered that this doesn't always work. Okay, so we do have a solution here, and we introduce this idea of a buffer that would keep track of which pixel color is coming from the closest triangle and store that information. So that is one of our solutions. Okay, so we talked about that a little bit last time, and here's just visualizing the Z buffer, or we call it the depth buffer sometimes, where the lighter pixels are closer to the screen and darker shades of gray pixels are further away. Okay, so just a little bit more review there. Okay, so let's talk about the transformations and just get a little bit more intuition as to what's going on here. Okay, so again, we really just have some individual point here. And so here's the point here, and it's being animated and sort of drawn to the right here. And we're applying some transformation to this point in a series of points such that it moves that point there, right? You can think of that as just an addition here to move us on our sort of Cartesian coordinate here by 1 unit. But we really need to transform it in 3D space. And often the type of transformations and things that we're trying to do in graphics applications are things like rotations or scaling, so making things bigger, rather than just simple translations here. So we're going to see how we can sort of change using a matrix, perform a series of linear transformations of a point across an X, Y, and Z space. Okay. And that's sort of important that we do this in a linear way, right? We don't want to hop or skip or do anything like that, and that we can manipulate things in 3 dimensions, X, Y, and Z. Okay, that's why we're using a matrix. Okay. So we have this nice little cheat sheet here showing off our different matrix or math operations here. Okay, but I want to give some more intuition as to how these things work here. Okay, then we can begin to manipulate how our scene works. Okay, or how our graphic scenes work overall. Okay, so again, recall that the diagonal when in the scale operation represents the X, Y, and Z components here. Okay, so when I'm performing a scale operation here, whether it's in one of these dimensions, here it is in the X dimension here, I'm making this object bigger here. Okay, so this is the matrix transformation for scale. Okay, so here's the equation here. So here's just a 2x2 matrix, and this applies. So in 3 dimensions, here it is. We'll talk about why this is a 4x4 matrix in a few moments. But here's the result of the multiplication that takes place. Okay, so here's another example that maybe will make clear the scaling operations too. And A lot of times in graphics, we'll use a clock as a good example because you can see if something flips or just, it's a recognizable object. But if we're scaling 0.5 in the x dimension and 0.5 in the y dimension, that's effectively taking all of our points here and crunching them down a half here, taking our point that was here, crunching it down in a half. Okay, so that's one way to sort of think about that. Taking all of our points here and halving them, okay, to get the scale here. Here's a non-uniform scale, so you can see taking all of our x points and halving them in this way, and taking all of our y points wherever they are. In this case here, these ones are at 0, so they don't move, but moving them up 1.5 units here. Okay. So that's what you're doing. You're multiplying through each of these points, your x points by 0.5, your y points by 1.5, and that stretches out or gives the appearance that you're stretching out the object when you do these to all of the points. Okay, some other transformations that we can do that are related that we didn't talk about are shear operations. So a shear or a skew is an operation that pushes an object sideways. Okay, it's skewing its direction. So note that this shear x moves points to the right in proportion to the y coordinate. So here's an example of that. So it's in the, it's a little bit easier to see an example here. And we can do this in 3 dimensions just as well. But the y coordinate here is where we are shearing. So we're not scaling anything. Maybe that's the easiest way to see it. So if we look along this diagonal here, these are each 1 and 1 here. But for the shear x, we're moving to the points in proportion to the y coordinate. And this, on the other hand, to the x coordinate. Okay. Let's just take a look at this. Here's an x shear. We're shifting all of the points by 1 in the x position here. So I'm just sliding things over. Okay, so I'm just grabbing the top of this clock and then sliding it over. Okay, and likewise here is the y shear example. So on the right side here. Okay, I'm just grabbing the points here and then lifting them up. Now, where would you use something like this type of transformation as opposed to, just moving a point? Well, for facial animation, for example, you can get a nice sort of shear, or sort of as you're lifting up points, have other points sort of move with some continuity here. So you can see this character sort of smiling where the upper lip is lifting. It's also increasing the lip size here, and you're gonna sort of getting the mimicking of how the folds on the face move in this way with this shear transformation. Okay, so it's almost an optical illusion too, how some of these work. But if you just sort of take a moment to just draw a line here to say, okay, how much did I, in the y shear point, how much did I pick up the this x point here? Well, it is 1 unit here. Okay, so if I perform this shear here, that aligns me here with this, y value here of say 1 here. Okay, so shears are not used as commonly, but you'll see them on occasion. But what you will see frequently is a rotation matrix. Okay, so that is, given some point or given a vector A, and then you say I want to rotate it by some angle here. So here's our vector. Let's say it's across here, and you want to rotate it up this angle so that it points up in this way. Okay, so we'll just look at them in 2D for now. Because that's a little bit simpler, but the things still apply in 3D. And here's the actual, again, 3-dimensional rotation matrices that we care about. Okay, so again, when you rotate your vector, it's going to produce a new angle. Okay, so you're rotating by some angle, and you're just taking all the points and then rotating them around some axis or rotating around some vector. When we do an x rotation, y rotation, or a z rotation, we're rotating around a vector that's either just pointing perfectly in the x direction, perfectly in the z direction, or perfectly in the y direction. So for example, again, I'll bring myself back here. But if you're rotating, doing a Y rotation, and you're doing your right hand rule, so remember what that was with your right hand and pointing your fingers. My pointer finger's the Y axis. So if I'm doing a Y rotation, I'm going perfectly around the Y axis. So you can imagine a planet, Earth rotating around the Y axis or my pointer finger. Okay. So that's just what's going on with the X, Y, and Z rotation. Now they can be combined, but again, it's just a little bit easier to look at these in 2D right now. And imagine that we have this vector here, and we're taking a point and rotating it about some vector. Okay, and here's our new vector here. So we can derive these nicely when we think of things in polar coordinates. Remember, we talked about that there could be different coordinate systems. So polar coordinates is sort of like our cylindrical coordinate system. So again, vector A has a magnitude from X and Y, right? So this vector here has some magnitude. That looks like it's roughly like 1, 1 or something like that. So it's in this direction. So we can figure out, if we want to compute the magnitude, say this is 1 times 1 plus 1 times 1 or something like that. That's about what this vector looks like to me. Then we can rotate. So any vector that we're rotating also has the same length here, right? This length didn't change. We're just rotating it, right? We're just changing the direction here. Okay, we're not changing the magnitude when we perform a rotation. That would be scaling instead. So it's the exact same thing. That's just something to keep in mind here. Okay. And if we want to convert things to polar coordinates, remember there's a conversion here. We're taking the magnitude that was our length here, or in this case it's r is probably the radius, right? We're in polar coordinates here, and then we're converting to x and or our x and our y. This is what we're doing the conversion to. Whatever our magnitude was, square root of 2 in the previous example, and then the angle that we are trying to rotate by, the angle of A that we're rotating. Okay. So this is our rotation, and whatever the result of this is, well, we can send this back into, or do the conversion back into Cartesian space and get our new x and y values. Okay. Here's one other way to sort of visualize this. Okay, so you have your x point and your y of your vector, or the x component and y components, proper way to say that. We computed the magnitude, and then here's our original angle, and here's the angle we're trying to rotate, whatever this phi is here. Okay, so we're adding those together. Here would be the addition in the sort of polar coordinate space here, where you can figure this out here. Okay, and these are your trigonomic identities. So maybe you haven't seen these in a while actually, but they're angle, sum, and difference identities. So that is what happens when you're adding an angle, if it's a sine, or adding an angle when you have a cosine. These are the identities to tell you how that transformation is changing, or how to actually compute a value there. Okay, so now I notice 4 components here, which is pretty cool. So if I'm doing the x and the y here, and then I can indeed sort of see where this matrix transform comes from. That is, if I look at these transform matrices, I can see that there's a cosine here, a sine, a minus sign, and a cosine here. So I'm doing 4 different computations here. Okay, the computations will change based off if you're moving in the x, y, or z slightly, but that's again just where this is derived from, so you can sort of see that in the transformation. Okay, so we're doing 4 operations here related to these operations here from our identities, right? For x, we have to do 2 things, 2 operations with cosine, sine, sine, cosine, cosine, sine, and so on. Okay. So here's an example, and it's easiest if you sort of focus on the point between 1 and 2, that is on our clock here, between 1 o'clock and 2 o'clock. And this matrix is rotating 45 degrees. Okay, so I'm going to take all of these points here. So there's a vector from my origin to this point, a vector to this point, a vector to this point, and then I'm going to rotate all of those, okay, by 45 degrees. Okay, so I have some other, so that's the rotation that I want to apply here. Okay. Okay, so that's just the example there. So for 3D matrices, again, observe the following. The ordering of cosine, sine, etc. They're all the same. So cosine, cosine, minus sine, cosine, minus sine, or where these fall rather. If you just think of these as sort of four things, you have your cosine, your sine, and your cosine. That's just a helpful way. You won't have to ever memorize these transformations, but again, I just want to show you that they're not disappearing. There's no magic really going on here. You know, the derivation is kind of interesting for how we figured out to use these matrices. That's the interesting part, but you know, nothing's getting thrown away or hidden in these transformations. And again, a 1 appears in the axis that you're about to rotate about. I think that's the other important thing for you to observe here. Just one, it makes it sort of easy so you can remember what's going on. But remember when we were scaling things, we had the x, y, and z dimensions. So look at your scale matrix here. That's where x, y, and z are. So it's just going to be fixed here in this dimension. You're not going to move, since you're rotating about the x-axis, you're not moving sort of any of those, you know, that's where you're sort of fixed here, okay? Okay, so here's something that's going to pop up towards the end of the class, but we're going to need to use these rotation matrices to perform some rotations. A common thing we will do is build a little solar system where you'll be doing some rotations. And this gets kind of interesting because you're rotating, you know, the sun rotates, the Earth rotates around the sun, and then we have a moon rotating around the Earth as well. So there's actually quite a bit of number of rotations going on, and you know how to compose those matrix transformations will be left for us for a later assignment. Okay, so let's talk about some more transformations and things that we're working on. So reflection, occasionally we like to reflect a vector. And this kind of gives us a mirroring effect. So you'll notice if we're reflecting about the y-axis, we are flipping all the x values. If we're reflecting around the x-axis, we are flipping all the, if we're reflecting around the y-axis, we are flipping all the x values. If we're reflecting around the x-axis, we're flipping all the y values, okay? And this sort of makes sense. So again, with a clock example, if we are flipping around the x-axis here, or excuse me, this is reflection about the y-axis because we're flipping on the y-axis. You can kind of think of this as a like door hinge, and then you're flipping the clock around that door hinge. Then you get this mirrored effect. You can see that everything's backwards. Yeah, that's why we're using the clock face for this example. Okay, so all the x points have been flipped because we're flipping around the y-axis. Okay, and likewise, the reflection about the x-axis is also similar. So we're flipping around, if you want to think of this as sort of your door hinge here, where this clock just falls straight down because we're flipping all the y values. If this is 1 here, now it is -1 down here. Okay, so you just flip the clock down. Okay, so here's an example for you to think about for a moment. Real world example. So here's some game here. What do you think is going on to create this effect here? Got this character and some things going on. What sort of transformations? And if you've paused and taken a moment to think about that, that's great. And, you know, it looks to me like, you know, and there's multiple ways you could do it, but it looks like the scene's being sort of reflected. So, you know, this character, again, if you can think of like just sort of him falling into the water here, that would sort of reflect him like a reflection from water. And then it looks like there might be some shear operation going on where they're moving the water sort of back and forth and performing a shear operation. And that'll sort of give a nice sort of wavy effect, okay? So wherever your pixels are, your points here, you just kind of shear them and that'll create some water effect. And it actually looks quite nice here, okay? So it's demonstrating some of the things some of the transformations that we've learned about, but it's also demonstrating, this idea of composition. That in order to get some of these effects, we have to compose multiple transformations. How do we do that? That's with our matrix multiplication, and we talked about that last time a little bit. Matrix multiplication and this idea of how to multiply matrices, but also that we can compose them and also that the order matters. Okay, and these operations are done in something called a fragment shader, which we will talk about later. So fragments are where we draw the pixels out. Okay, so again, you can compose matrix transformations. That's the real power of them. That's what makes them powerful. They're easily composable or easily parallelizable in our GPUs. Okay, so and the keynote though here is if we have some vertex here, vertex v3 here that we're transforming, and we want to scale the vector and then rotate it. Well, we do this sort of backwards, if you will, okay? So we first scale the vertex and then we rotate it. So we're reading this right to left. Okay, that's how we do our transformations. That's actually very important. It's important enough. Let me give it the sort of gold star treatment here. And it's just so you can see me do it, that we read our transformations left to right here, okay? Or excuse me, right to left, right to left. Read our transformations right to left here. So we scale the vertex first, then we rotate it. So we're working backwards, which is going to be a little bit strange for us, but that's how we properly compose our matrices together. So that we scale the vector first and then rotate it. Otherwise, if we flip them, then we're doing the opposite, where we would be rotating the vector first and then scaling it. Okay. So here's an example of the different operations that we have here. So if we have this clock here, and if I scale it first, so this is the scaling. If I go to the right here, shrink it down and then rotate it, this is what happens here. Now I could scale this and then also rotate it here. This is still reading us right to left here. So both these operations are going to be okay. Okay, so if I do things a little bit differently, and I don't consider the order here. So on this side, I guess the parentheses, the grouping doesn't matter here because it's multiplication of how I'm moving this vector v1 to be a new point here. But here's a nice example of the order mattering. So if I scale first and then I rotate, I end up with this sort of transformation where I sort of shrink it down and then rotate it. I get this transformation. Versus if I rotate it first, well, I rotate the clock and then I squish down the clock from how it's been rotated. So I'm just squishing down in one axis here. It's kind of interesting that we get two different outputs here. So again, that's why the order matters. Again, we're just transforming these points or moving them in a different direction. And you could sort of do this example. Again, I'll bring myself on the screen here for a moment. And, give yourself two instructions to do. Rotate and walk forward. Okay, and if you flip what those directions are going to be, so you can do this with a friend or a roommate, and one of the times, tell them to go to a specific place and face a specific wall, and tell them, rotate 90 degrees to your left and walk forward one step. Have them do that experiment. And then do the same experiment. So they start in the same position. Again, you can tell them walk forward one step and then rotate. They'll end up in different orientations. Okay, so that's one way to remember how the order matters. Okay. So here's just another graphics example. This animation, they're showing you the translation first and then the rotation. Okay, and then again, just think about this as, right, you're at the origin, you're translating your point forward, and then you're rotating about, well, where that middle sort of point is, or all of your points around this vector from the origin. Okay, this will give you in a different location than if I had rotated first and then translated somewhere else. Okay. So if I would have rotated first by, it looks like, 0.12 radians or whatever the units are, then I would have still landed here, but just in a different orientation. Okay, you can do this experiment if you've done some 3D work before and recreate this otherwise. Okay, so you might have noticed that we haven't talked about translation yet, because in our 2D examples, there's actually no way to move an object, which seems kind of funny. Because we can only really scale and rotate the object. This below equation isn't going to work with a 2x2 matrix because we need to do some sort of other bookkeeping to move our points here, right? We've already sort of taken up the middle points for our scaling, and then sort of how to rotate those points. So the trick is to add another vector for translation. So you can see we added this additional dimension here where we have x and y for x translation and y translation here. Okay. In our third column here. This is a trick of what's known as, we use affine transformations in computer graphics, which preserve the ratios and distances. Okay, so if we're going to move something further after we've already scaled it or rotated it or whatever, we want to sort of preserve the sort of perspective there. Okay. So you'll notice there's another last point here, maybe what you'd think of as z, but it's just a 1 here. And this last coordinate here really represents movement or position. If it's 0, then we multiply through, we're representing a vector or some sort of displacement. Okay. This again allows us to distinguish between some transformation, rotation, scale, translate, or some other vector operation. So we just make this 1, and this sort of preserves all the other stuff that's going on here when we do the actual multiplication. Okay, it's not going to disturb these values. Okay, it's just the identity. Okay, so here's an example of transforming a 3x3 matrix by some shape here. So here's our matrix, and we're multiplying by x, y, and then we have the 1 here, right? So we do the dot product. We multiply these values by this, these values by this, these values by this, and this gives us our new transformation here. Okay, so how much we have translated, this is the new vector here. Okay, so this is translation. 1's along the diagonal because we don't want to scale anything or change anything. Here, this is just the identity, and then our x, y, and z points. Okay, so we've been going on for a little bit, so just go ahead and give yourself a break if you need it, and then we will resume. All right, if you've given yourself a little break, we can resume here and talk a little bit about viewing, just to get a little preview here. Because, again, it's been useful to think of transformations we've been performing as just moving, scaling, rotating an object or a point, but we can also think about it as moving the world around us. Okay, so regardless, I can think of sort of, if I have this scene here and I want to translate a point back -1, 0, well, I can think about sort of moving this way where I transform the point here, so everything's sort of relative to this axis here, or I can just move the whole world to that point here. Okay, so notice how in this example, I just took the axis and I just slid it over here. Okay, and that effectively did the same thing. Now my, relative to where my origin is, this point's still 1, 1 now, versus this where I just took the actual point and moved it back. Okay, so with our math knowledge, we figured out how to solve this problem, or viewing a 3D world on a 2D surface or monitor, or at least talked about the stages enough. But we need to keep in mind some other things like the camera position, the camera orientation, our field of view, how many pixels we have, and so on. Okay. So we're going to have a virtual camera in our world from which we view our scene as our eye. So our human eye, the thing that takes in light and builds the images and so on. And we'll talk a little bit about this, but our eye is just how we see the world. So again, it's just our virtual camera. Teaches us how the image is constructed. Okay. And some other things to keep in mind. We're going to try to render things at 24 frames per second at least. That's what movies are shown at, sometimes 60 frames these days. Video games, 30 to 60 frames. VR headsets, 90 frames per second, etc. But anyway, back to this problem of what does our eye see. Our eye is going to sit at the origin of our scene and then render things in a chopped pyramid. So, depending on how we want to move the world around, if we want to move the entire world or just move all the objects, that's going to be up to us. But typically, it's a little bit easier if we just move the entire world, which sounds weird. but it's less work than saying, hey, all the points, need to move towards me or away from me or whatever we're translating them. Okay. But our view frustum is how much our camera can see of this world here. So it's a chopped pyramid. So meaning we just sort of chop it off at this point. The near plane is the closest object that we can see. So there's some space that we can't see here. I'll go ahead and pop up on the screen here. So it's kind of like if you take one of your fingers and move it closer and closer to you, eventually the finger disappears, right? This is sort of your blind spot, right? Or the vanishing, I don't know, can't remember the right term, but not the vanishing point, but it's just sort of the blind spot where you move it close enough because your eyes are sort of converging, then you actually can't see that point here. So you might have to do this experiment a couple of times, keep your eyes open, and see if you can take your hand, your finger, or some object, and it'll eventually disappear once you place it close enough in front of you. And then the far plane, on the other hand, is stuff that, once you just can't see it because it's too far away, right? This is stuff we don't have to bother rendering or drawing into our screen because it's just too far away. Okay. Then objects that aren't visible. So we're looking in this direction here. We draw these objects, maybe part of this object, but objects that are too far away, we don't draw. Objects that are to the side or periphery, we also don't draw here. Okay. So we have our camera or eye transformation. We call this eye space or the view space that moves the camera to the origin and sort of orients itself in some direction. We have the projection transformation, the clip space that removes various points here that aren't visible. That's these points here for bullet number 2. And then we have our viewport transformation, which is going to map all of these pixels to some perspective range. Okay. GL viewport is going to be the OpenGL command, and then your homework, you'll look at doing this. Okay. So again, here's just the 3 main transformations. A visualization, moving something from object space, so this sort of local coordinate system, to the model transformation where we say, hey, I want to move R and rotate it and do those transformations. So here it is. And then we view this R here from our camera. So then it'll have some other orientation depending on where we are in the world, our camera. Our camera has this sort of perspective view of this object. Okay. And we do this projection transformation, which eventually puts it onto a coordinate system such that it's on our in this normalized device coordinates, such as 0 to 1, a range of that, and then we can put that onto our screen, which is the pixels. Whatever your resolution of your window is, that might be the range of these pixels that we apply here. Okay. So one thing to note in this last stage too is there's 2 different ways that we can do this projection. There's at least two common ones. Where we do perspective, that's what we're going to aim to do. So we see things like we see them in the real world, but you can also have this oblique or orthographic a projection which makes all the points, regardless of how far away they are, appear the same distance. So you get this kind of weird rendering, but it's actually useful for architects because then you can tell how long a line is. And you can see like the dimensions even if they're far away, so you can measure with an actual ruler to make sure everything looks right. Okay, so those are our two sort of use cases. We talked about having perspective with the train tracks, right? Objects that are further away appear closer together. This is known as foreshortening. Objects are getting smaller and smaller, but they appear to converge, but we know that's not true if you've ever ridden on a train track on a train. And here's the example of the orthographic. So this is in the drafting software called CAD, where we actually get to draw things, and you want precise dimensions. You want to be able to see those precise dimensions regardless of where you're viewing the object. Okay. So again, here's just that perspective, that viewing volume. We call it the view frustum. It's a chopped pyramid. We can't see objects that are too close, objects that are too far. We can't see, but instead we have this chopped pyramid here, where any object that falls in this is what we are able to observe. Now, when we have this plane here, we're computing the distance from some object here and figuring out, where does that object fall? So if it has this distance here, that's its z value, that's where it falls. And depending on where the object is or how far away it is, we are able to divide our y by the distance. Okay, so our x and our y. So if this object here, this train track's really, 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 really far away, we can divide x and y by its distance and get perspective. Okay, that's roughly the transformation that you can do. That's roughly the transformation that you're going to do in your lab. Okay. If it's useful, you can think of the perspective view volume as rays casting onto the screen, onto each pixel, and then figuring out where they are, how big they should be, and so on. That's just another way to think of it if it's useful. For the orthographic or oblique projection, you can think of it the same way, except you're not coming out with the rays in this sort of projection here, right? And the longer your ray is, right on this corner here, because it's coming at an angle versus straight on, that's how you'll sort of shift the distance or whatever this distance is, right? This ray on this side is going to be a little bit longer here. So to hit this point here, so that'll also create the perspective versus the orthographic perspective where everything's the same distance, okay, from your eye. That's what E is here. Okay, so once you've chosen a projection, so ours is going to be perspective. We want to see things in 3D and sort of accurately, like in a simulation in a game or real world, bringing in real world data. We can move our eye, that's this guy here, or by eye I also mean virtual camera, around in the world. And our camera is just another coordinate system that we can orient. So E is the eye gaze position, okay? So where we are in the world. G is the gaze direction, where are we looking? So you can see this character sort of looking around in this virtual reality simulation. And T is the up vector, where is up in our world? So where is up? That's where I'm rotating around when I am looking left and right and all around in this world, okay? So we need to know where up is so we can rotate about that point. And you can see the camera sort of moving here on the upper screen. Okay, so where I can see again, or how wide that is our field of view. That's the width of our eye gaze. That's how wide that chopped pyramid is, the view frustum. And this angle is theta divided by 2. That's the angle of our field of view. Because what we do, and what you'll see in your lab, is we divide this view into 2, make a right triangle, and then we have a 2 right triangles essentially, and then we can compute the distance to these points. Okay, so a wider field of view gives us more stuff that we can see, but it also might distort our what we perceive. Again, normal field of views are like 90 degrees. I guess they range person to person, but something in that range would be normal. Okay, so wrapping things up here with a few videos, because it's nice to hear or see others' perspective. I've been talking about perspectives. Here's a few more examples, just talking about and illustrating the perspective camera. This is a nice one, talking about the eye and just how objects that are further away, we can divide by the z distance to create perspective and the height. A little bit about that camera. Again, this is a nice one that illustrates just what the eye position is, the up vector, and the gaze or the direction. And some on the translation, rotation, and or these two matrices here. I guess just translation and rotation that I've included. Okay. So with that, your in-class activity is open as well, so you should be able to take a look at that. Your next homework will be pushed a little bit later if you're watching this right at 6 o'clock. And your lab, however, is available, and we'll take some time to catch up on Piazza and do all those things. So looking forward to talking with folks soon, and have a great weekend.